Okay, so this video is going to be on differentiation. Now, the first thing I figured I should start with is to point out that differentiation literally means to find the gradient. Okay. Now, another thing I would point out is that the gradient, another word for the gradient is also, could be the rate of change, and I'll show you what I mean by that in a moment. So, if we're dealing with a nice linear function, like so there's a graph axis, there's my nice linear function, then the way in which I would suggest that you find the gradient is to choose 2 points on the line. We draw a right angled triangle, and then the gradient is basically, we take the difference in height, I'll call that dy, we take the difference in x, call that dx, and all we do is we work out dy divided by dx. Okay, and that's all you do for a linear graph. Now, the reason why I said that another word for the gradient is the rate of change is because if you think about what's actually happening here, you're taking the difference in height and you're standardizing it by dividing it by difference in x. And that will tell you for every 1 I go across in the x, how many I would go up. So basically, if the gradient of a function, say, is 3, then it means for every 1 I go across, I've got to go up 3 to get back onto the line. Okay, so that's basically what gradient is. It's the rate of change of y compared to x. Okay, now that's all very well and good. Excuse my voice. But what happens if we're not dealing with a linear function? Now, this is where it gets really, much more complicated. Okay, so let's say that we're talking about a generic function that is not a straight line. Okay, so I'm going to draw this. It looks a little bit like an exponential function, or a quadratic maybe. Okay, and what I'm going to do is I'm going to say this is the graph y is equal to some function of x. So this is completely generic, okay? This could be a quadratic, it could be a cubic, it doesn't matter, okay? So that's why I'm using function notation. Now, if I want to, the first thing I would say, right, is looking at the steepness of this curve, because that's another way of thinking about gradient. Well, the steepness is constantly changing. I mean, here it's kind of like that steep, whereas here it's obviously steeper. Okay, so this is what we're going to do. I'm going to try and pin us down. I'm going to try and calculate the gradient at this point down here. Okay, so let's say that that's got an x coordinate of x. Now, because the function is y equals f of x, that means that this y coordinate will be f of x. So what I'm then going to do is I'm going to choose another point over here, and I'm going to say that this is x plus h. So basically I'm saying this gap here is h. You know what? Let me change that. X plus dx. What makes that dx? Okay, so that's the difference in x, right? Well, okay, well now I've got to figure out the y coordinate. So I'm talking about this point up here. So I've got the x coordinate. The y coordinate will be the function of x plus dx. And then I can connect the two. So, straight line. Okay. So I might not be able to calculate the gradient of this line, but I can calculate the gradient of this one. Okay, so the way in which I would do that is I would, again, just create my little right angled triangle, like so, and I would say, well, what's the difference in y? Well, it'd be this y coordinate, take away that y coordinate, and the difference in x, which will be just dx, okay? And I can say, well, look, remember, the gradient is difference in y divided by difference in x. So I can say the gradient of this line here is going to be dy over dx f of x plus dx minus f of x over dx. Okay, now that's very well and good. But obviously, the gradient of this line is not the same as the gradient of this line. And this is the line I really want. This is the gradient of this curve at that point. So in order to get this line to be sort of like closer to this, I can say, well, what would happen if I made dx even smaller? So let me just sketch this out again. So my curve is kind of like that. There's my point here. So that's x. If I made dx a bit smaller, there's my gradient I'm trying to find. There's the gradient that I'm actually calculating. Then hopefully you'll see that this line is actually closer to this line than this one was. In other words, if I bring this point down that curve and I keep the straight line connecting the 2 points, eventually as I get closer and closer to here, this line will become the same steepness as this line. Okay, so the ultimate value really for me for d of x is actually to let dx tend to 0. Now I can't let dx equal 0 because obviously this is a fraction, which, you know, 0 on the denominator of a fraction doesn't sort of like bode well. Okay, but I can let it tend to 0. Okay, now this is basically the fundamental principle of differentiation. Now the good news is when we start getting onto the questions, you do not need to go through and use this every single time, but it is incredibly useful to know what this is and know how to apply it before going on to standard sort of like, you know, differentiation style questions. Okay, so excuse that. Sorry about that. Okay, so I'll give you an example. So let's say that we're talking about a specific graph now. Okay, so rather than the abstract y equals f of x, this is the graph y is equal to x squared. I'm going to calculate the gradient. Okay, so the way I would do it is I would say, well, look, if I let f of x equal x squared, I would say, well, look, I worked out last time that the dy, the gradient, dy over dx, will equal to the limit as dx tends to 0 of f of x plus dx minus f of x over dx. Well, okay, well, swapping the function notation for x squared, that means that I can write that dx over dx, sorry, dy over dx is equal to the limit as dx tends to 0 of, well, f of x plus dx. I just take what's inside the brackets and I put that in for x squared. So it becomes x plus dx squared minus, now f of x, that just means, well, I know what f of x is x squared over dx. Well, I can expand and simplify now, right? That means dy over dx is the limit as dx tends to 0 of x squared plus 2x dx plus dx squared minus x squared over dx. And then finally, well, x squared take away x squared. That dx can cancel with that dx and one of those dx's. And then finally, remember, dx is going to tend to 0, so we'll treat dx like 0. So I'm just left with 2x. Okay. Now the significance of this is that if you look at the gradient of the line y equals x squared, the gradient will always be double whatever the x coordinate is. So if the x coordinate is 4, the gradient will be 8. Okay. Now that also extends to on the other side. If I extend my axes, if the x coordinate is -3, then the gradient will be -6. Okay, so what I'm going to do now is I'm actually going to generalize this a little bit for you. All right. Now later on, you'll be able to prove this a little bit more sort of like conclusively when you see the binomial expansion. But at the moment, I'm just going to hopefully convince you of a pattern. All right. If I do the same thing for, say, y is equal to x cubed, this is what will happen. I will get dy over dx is equal to the limit as dx tends to 0 of x plus dx cubed minus x cubed over dx. Now when I expand and simplify that, I get limit dx tends to 0 of x cubed plus 3x squared dx plus 3x dx squared plus dx cubed. minus x cubed. Well, and all that's over dx. Okay, so that cancels with that. That cancels with one of those. And then dx tends to 0, so all that can go, all that can go. All right, that just leaves 3x squared. Now, if you compare that, let me just show you something. If we're differentiating x squared, we get 2x. If we're differentiating, we get 3x squared. Okay. What's the pattern? Well, the pattern is, if you want to differentiate a polynomial, then all you need to do is drop the power. Okay, so let 2 comes down and reduce the power by 1. Okay, so that's kind of like our summary for differentiating polynomials. You drop the power, and then you multiply by the power, and then you reduce the power by 1 in that order. So if I ask you to work out d over dx of, let's go for something a little bit harder, 4x to the 8, it will be 32 x to the 7. If I ask you to differentiate 10 x to the minus 3, it will be minus 30 x to the minus 4. Okay, and one more thing. If I ask you to differentiate something that has a constant, then you differentiate the algebraic part. The constant, oh, that should be a 6. The constant just disappears. And it's actually quite easy to think about why that is, right? Because if you come back to, say, our x squared example, if I was actually differentiating x squared plus, say, 10, then that would shift the graph up. Now, whereas it's changed the height, it hasn't actually changed the gradient. Okay? And that's pretty much it. Now, I would encourage you to watch the applied questions very carefully, because there's a lot of, suffice to say that you can never get enough practice at this. Okay?